Right, hi everyone. I think we should start. So today we have Dr. Florian Regnault, our very own, as part of the CME group in UNH, where he works primarily with Nada, Noe, and then also Charlie in the corner here. So yeah, I first met Florian, I don't know, it was quite a few years ago now, at a conference in Argentina. It was like a nice excuse to see this like total solar eclipse that was occurring at the time. But yeah, and it was just before I was bitten by a fox, which people became aware of last week in the same seminar introduction, so that's nice. But yeah, today we'll be talking to us about magnetic field structure of CMEs. Before then, he completed his PhD at it's French, Institut d'Astrophysique Spéciale, with Miko Yapia. Yeah. And yeah, so I think I'll hand it over to you. I think hopefully we'll have a nice more interactive seminar today, so we're all in person, and of course online as well. Sure. Please raise your hand or write in the chat.
So so thank you.
No, thank you.
So I have something if I were to talk alone for I can stay for at least 45 minutes. But the way I seminars, I actually want to discuss with you. So I have some slides. If I don't go through all of them, that's all right, because I have some kind of summary rush or messy different methods that I'm going to show to explain to you in order to investigate the magnetic field structure of CMEs. So if you have any question, that is not a very global one that can be actually quite hard to answer, please ask. And if you have some more discussion, more deep question about some stuff, we can talk about that at the end. So if you have any questions, please ask. Okay, so let's start. So my name is Florian Regnault. As you will hear, I come from France, where I did my PhD. And I arrived at UNH a bit more than 1 year ago. It was late October. And today I'm going to show the work that I've been doing during my PhD in France, and also the work that I've been doing here at UNH, investigating the magnetic field structures of CMEs. Here you can see collaborators that I used to that I'm still working on for most of them, working with them. And before going into details, I'm going to first do a bit of introduction to solar physics and back up to talk about the solar atmosphere. So the outer part of the solar atmosphere is called the solar corona. You can see the solar corona during this kind of event where you have what we call the solar eclipse, where you have the moon that will hide the very bright solar disk, and then it will allow you to observe the faint atmosphere of the sun. And what you can see is that actually these lines that you can see here correspond to the manifestation of magnetic field lines, where actually you have some region of open magnetic field lines that are close to the pole, the magnetic pole of the sun, and then you have this region where actually you have these closed magnetic field lines here that correspond more that are closer to the equator of the sun. So you can see the magnetic field actually structures the solar atmosphere of the sun. We also observe the emission of particles that we call the solar winds. That's a steady emission of particles, and sometimes some events that some eruption of complex magnetic structures that we call CME will disturb the properties of the corona and of the solar winds. And so CME stands for Coronal Mass Ejections, and that will be the main object that we're going to talk about today. They correspond to the ejection of plasma and magnetic fields in the interplanetary space, and we can observe them in multiple ways. First, you have on the left-hand side here extreme ultraviolet images of the sun, where you have this kind of structure here that is called a prominence. So this is a magnetic arch that is able to hold some material. This is what you can see here. And this kind of structure can be stable in the solar atmosphere for a few hours up to a few days. And then sometimes they can start to erupt, as you can see here, and then eject all the plasma into interplanetary space. Well, now when they start to propagate in the interplanetary space, you're not able to observe them with the CME images, and then you start to use what we call coronagraph, which is basically a telescope. You just create an artificial solar eclipse where you just have this disk here that hides, as in a solar eclipse, the bright solar disk and allows you to observe the solar corona. And then during a CME, you'll have this eruption that you can observe here. And given the shape of what we observe here, like this halo stuff, so this is what you call the halo CME, it tells us actually the CME is propagating towards the Earth. During their propagation in the Earth space, they may reach Earth, as I just said, and it will have an impact on our technology or on the Earth. Actually, most of you here probably heard about CMEs mostly by the interaction with the Earth sphere, for instance, with electricity blackouts that can occur during when a CME reaches the Earth, but also with the northern lights or polar aurora, so like the green lights in the sky during geomagnetic storms caused by the arrival of the CME close to the Earth. And today, I'm going to focus on the CME, the study of CMEs during their propagation in the temperature space. You can see on the right-hand side of this slide here, a schematic of the structure of the CME during its propagation. You have in purple here, so it corresponds to the magnetic field lines of the magnetic ejecta. This shape that you can see here, I'm going to go in more details after. This is what we call the flux rope. So we often use the flux rope to describe the magnetic field structure of the CME. And so the purple part that you can see here, this is what we call the magnetic ejecta. So this is the magnetic structure that is being ejected from the solar core. Then during its propagation, so a magnetic ejecta or any, if it is fast enough, it will accumulate some solar wind material ahead of it, and then form what we call the sheath area. And then it will heat and compress. It will compress the solar wind material that is just ahead of the magnetic ejecta. And then sometimes ahead of the sheath, we observe a discontinuity in the physical parameter that sometimes corresponds to a shock. And in order to study, mostly right now, what we have to study CMEs during the propagation is what we call in situ measurements that correspond to actually spacecraft that are in the interplanetary space and that measure local properties of the solar window or the CME. That means that we only have like local measurements of this 3D structure that we have here. And this is something that we're going to discuss a lot today. So I'm going to show an example of the CME seen by the ACE spacecraft, which is a Lagrange 1 point. So this is just right here between the Earth and the Sun, but very close to the Earth. So we have on the left, right-hand side, the magnetic field first as a function of time during the passage of the CME. And here you have the velocity and the temperature. And just want to define something you'll be hearing. I'll be talking about the magnetic and the plasma properties of the CME. What the magnetic, of course, refers to the magnetic field, and plasma properties indeed will refer to speed, temperature, or the density. So this is like the two main things I'm going to talk about today, but mostly the magnetic field. First, what you can see in the time series that we have here, we have this discontinuity in the parameter. Actually, that corresponds to the beginning of the sheath area that I was describing just after. You have the discontinuity. And after you have the high temperature and velocity and magnetic field inside this green area that correspond to the solar wind material that is being compressed and heated due to the compression of the propagating magnetic ejecta. And we also observe the noisy magnetic fields, like very noisy magnetic field, like in particular its components inside the sheath area. Then just after this area, we have what we call the magnetic ejecta, where we have this low temperature in this region. So this is the blue part here. We have monotonic decrease of the speed, so it follows almost like a linear trend. So this is interpreted as the trace of the radial expansion of the magnetic ejecta. You have the front that is going faster than the rear of the magnetic ejecta, so it expands while it propagates. We also have a smoother magnetic field compared to the sheath area. But this is because we cross a more coherent magnetic structure compared to the sheath. And then we also have like very important signatures that we don't observe all the time, is that this is what we call the smooth rotation. And this time it will be for busy component. That corresponds to this change of sign, this smooth change of sign of the busy component, which is in red here, where we go from minus 10 nanotesla up to around 10 nanotesla. So we have like this change of sign that is actually characteristic of the flux rope. Then I'm going to talk about that just after. Okay, so if you talk to people, if you ask someone working at CMEs and you ask, okay, what's the shape of the magnetic field of the CME, he will answer you, well, flux rope. But the thing is that there are lots of models of flux rope. But as an example, I'm going to use a very, very famous one that is used by that has been widely used to describe CME magnetic field structures is called the Lindquist model. So you can see here a schematic of the magnetic field structure where you have these helicoidal or twisted magnetic field lines around the axis that you can see here. And one interesting property is that actually we have more twisted magnetic field lines on the outer parts of the CME, whereas the magnetic field lines closer to the X is actually more less twisted in some way. And so this model has been like developed in 1951 by Lindquist and then adapted to CMEs by Lipping in 1990. And the fact that the in situ measurement that we have, as I discussed before, are just a local measurement. So when your CME is propagating and crossing, and the spacecraft is crossing the CME, you only have a local measurement of the full 3D structure. So you only have this information here. So it's actually very difficult to have an idea of the global shape of the CME, to have a global shape of the magnetic field structure of the CME. And this is why people developed a theoretical model to deduce the global properties of CMEs, assuming some shape of the magnetic field structure. And this is what we did using the Lindquist model. And then using those models, you can deduce the orientation of the flux drop. So that would be how tilted is the flux drop when it crosses the spacecraft. You can also get the size of the flux drop or the radius, that would be this size here. Or you can also have what we call the impact parameter of the spacecraft, which is basically how far you are from the axis of the flux drop. So now I'm going to share an example of a fit that allowed us to get some properties, global properties of the flux drop. So we have here the magnetic field magnitude and its component here, that is in black, that's data, and then in red. So this has been done by Wenyu, which is a postdoc at UNH here.
Sorry, can you go over the coordinate, like how the coordinates are defined?
So yeah, sure, you're right. So that's the magnitude, then X, that's where, let me show you in this schematic here. So finite from, so we have the sun here, the F here, the X would be towards the Earth, and then you have Z towards like, that will be out of the one here out of the ecliptic plane, and then you have the Y, which is either here, just like to go like a direct, like, you know, the right hand rule. Yeah, so sorry, here, so you have the results. So in black, you have the data, and then the different components of magnetic field, and in red, you have the result of the fit. And here you have the cross section of the Lindquist model, actually, where you have like in red, like the actual magnetic field, which is in BY, in that coordinate system coordinates. And you can see that's actually, it matches quite well. We have like, for instance, in the BZ component. So here you can see that the BZ is pointing downwards, and you can see that here we start from a BZ that is negative, and that is negative and positive. So you have like, this is a trace of the smooth rotations. This is why the smooth rotation is often interpreted as a trace of the presence of a flux of signatures. Then you can also observe we have a nice match in the BY component, which is the actual one. So this is the one working. That's where we have this increase closer to the center of the magnetic eject, and then it starts to decrease. But the thing is that some CMEs actually, and the cross section of CMEs can be distorted during the propagation. This is something that we found in a study that we did during my PhD, but also some simulation performed by Camilla Scolini, another postdoc at UNH, showed that it's not that simple. Some CMEs may have this cross section, but most of them actually will not have that nice circular shape during its propagation. And actually, now I'm going to show you the result of the fits, but using another but this time not with this nice bell symmetric shape, but this time having a bell shape, but which is shifted toward the front. And what you can see that this time actually the fit doesn't work very well, but this is expected because one of the assumptions of the Lindquist model, or the model that you have here, is to be symmetric. And in that case, what the shape of the magnitude of the magnetic field tells us, actually there might be some compression of the magnetic field ejecta voltage. The core is shifted toward the front of the magnetic ejecta, and then the compression of the magnetic field lines increase the magnetic field at the front of the magnetic ejecta. So that's one interpretation of this profile that we observe here. So symmetrical assumption or circular cross-section might not be justified for all CNEs. But now we can, like, over more than 30 years that we use this model, some other people actually developed more refined model, actually try to have more degree of freedom given the shape of the cross-section of the CNE. And this actually, Emma did this, just use different models using only one CNE that you can see here. So this time this is RTN. That's basically the same system coordinate, you just do a 180-degree rotation around the Z components. So instead of having the R toward the sun, the R is just in the other direction. That's right. And then if we see the result of the, so you have three different shapes here. So you have this time in purple, it's not a circular cross-section, it's an elliptical one. So that it allows you to have some compression of the magnetic ejecta. Then you can also have what we call the kinematically distorted, so that this shape could be due to interaction with the solar wind, where if you have some solar wind pushing just after the magnetic ejecta, you could have some compression, more compression at the back than at the rear. Or you can also have this very distorted magnetic structure that you can see here, due to the fact that the solar wind during the solar phase, during the quiet phase of the solar cycle actually will be faster at higher latitude, and then it will cause this very distorted shape. And actually what you can see is that the blue lines actually is the one that matches the best the three components of the magnetic field. And so this is actually it can be very useful to have that kind of different models that can give us information about cross-section. But there are actually some issues with reconstruction method, actually some strong limitation that I'm going to show you. But first, Nadal had that, so in 2011 and 2018 showed that there are actually some large inconsistencies in the fitting methods for the, so we use different models, but for the same CNE, and we don't find exactly the same results. That's kind of an issue. Then the results of the fit depends on the magnetic ejecta boundaries. So just the boundaries itself, like just choosing where does the magnetic ejecta starts, when does it ends, it's already an issue in the community. Like people basically do not agree where should it start, what is it not, because most of the time it's not that simple. But then given their boundaries that are not that's certain in some way, then some fitting methods actually are quite sensitive to the choice of these boundaries. And then most of the things that we have are studied with single in situ profile. So we only have one cross of the 3D structure. And that raises one question, that is a local in situ profile representative of the full 3D semi-structure? And that's I don't have the answer. And it's probably yes, but the question then yes up to a certain point. And the question is, and the thing that we have to find is up to what scale? What scale it makes sense to have, like, to what scale, one local measurements, what would be the coherent scale? But this is still work, like with some stuff like we're currently working on. Okay, so this was about the reconstruction methods. So just trying to fit theoretical model on the data and then to obtain some local properties on the magnetic ejecta structure, right? So now I'm going to, this time, using another method, which this time is more about statistics. So instead of having one CNE and trying to fit different model to get information, well, let's try to take all the CNEs that we have, or as many CNEs that we can have, and then try to do some statistic with them. But the thing is that this is a magnetic field of the CNE that showed you before, like with this nice bell shape. But if you take a look at different CNEs, actually, you will almost never end up with the same magnetic field profile. This time you have this bell shape here. Here you still have kind of this bell shape, but you have these small features here. And this one is just straight line going down, but this is still a CNE. Like we do observe in the other physical parameters that there are some CNE signatures there. And so that raises the question, well, what do they have in common? And this is also why one's limitation when you study only one CNE, because you may have a lot of different things going on that are just small scales that actually are, right now, our models are not able to capture. So this is why we want to do statistics. That, okay, let's take all the CNEs that we have at a certain distance from the sun, and then let's apply a statistical method, which is called the superposed epoch analysis. The idea is quite simple, just to take all the profile, and then you superpose them. just a little warning, it will get quite technical for like the 2-3 coming slides, but the result of this, the idea behind is just simple. So if you don't follow very well, like for 2 following slides, don't worry. So superposed epoch method, you just like do a normalization in time, because as you can see, all the CMEs do not have exactly the same duration. Some are shorter, some are longer. So just like do normalization in time. You do time binning such that all the CMEs actually have all the profile have the same number of points. And here I just show you the example with free profile, but we can do that with n profile, and preferably n would be quite a large number, because it wouldn't make more sense to try to do a statistical study with just 3 points, right? So actually, this is what I did during that PhD. That was part of my PhD, was to do this kind of study for around 300 to 400 CMEs that we observed close to the Earth. So using the AIDS data, which is close to the Earth right here, at Lagrange point. And here we can see what we call the stacked histogram. So which is the evolution of the distribution of magnetic field as a function of time, with darker area that correspond to more probable values. So here you have the sheath region, here you have the magnetic ejecta, and you can see that in this part here, which is the measurement of the solar wind before the arrival of the CME, you have this dark area here that suggests that mostly the value of the magnetic field before the arrival of the CME is around 5 nanotesla, right? Now, if you get to take a look at the magnetic ejecta and therefore its temperature, so this is the second row here, we have this very dark area for very low temperature. And this is one of the CME signatures I described to you earlier. So that showed actually most of the CMEs that we have in our sets have a low temperature inside the magnetic ejecta. So this is in some way already some kind of statistical results, but it's hard to quantify something using this kind of profile. And this is why right now some people actually, and until, yeah, mostly when people have a distribution or have a set of parameter, have a set of points, and what they want to do is to compute the mean and even sometimes the median, therefore a bit we like to have different values. So we first use the mean and the median. This is mostly what has been used. You have in yellow the mean, and in median, in purple, imagine that, whatever, you have the median. But what you can see is that, again, if you focus on the temperature inside the magnetic ejecta, well, the median, the mean and the median does not match very well with this very dark part that you can see here. That means that if you use, for instance, the mean value of the median value inside the profile, you will overestimate what you define as the most probable value of the temperature inside the magnetic ejecta. Was that clear? Perfect. So this is, and so now if you take a look at the distribution, let's say for the magnetic field, but that works for the other parameter, actually they have this shape here, which is an asymmetric distribution that is well fitted by Regnault distribution. And this is something that was used by Rodriguez in 2016. And as we can see that since the distribution is asymmetric, because of the extreme value that you can see on the wing here, the right wing, the mean and the median are both they are both sensitive to these extreme events that you can see here, extreme values. And this is why actually in the study that we published in 2020, we computed what we call the mode, or the most probable value, which is just location in magnetic location of the maximum of the distribution. So it just gives us, in the end, the most probable profile for the magnetic field, the density, the temperature, and the velocity. So here you have the 3 different values I was discussing before. So you have, again, in blue, the mode, the most probable value. In purple, you have the median, and then in yellow, you have the mean value. And if so, now it's the end of the technical part. So if someone asks you, or if I were to tell somebody what does a CME look like typically, that would be the answer, because this is a statistical study on more than 300 CMEs, and this gives us the most probable profile of the magnetic field, the density, the temperature, and the velocity. And we can see all the main features that I was telling you about at the beginning of this seminar. First, we have we have this increase of density, temperature, velocity, and magnetic field inside the sheath area due to the compression of the solar material. We have this low temperature in the magnetic ejecta, and you can see that this time the blue line actually is way better estimation of the temperature inside the magnetic ejecta is followed very well, this very top part that you can see here. And something that is quite interesting, and it's something I'm going to talk about after, is actually a magnetic field is asymmetric. And the asymmetry of the magnetic field is something that is quite studied right now. And you can see that mostly CMEs are actually asymmetric. It's not that nice bell shape that we observe, like the thing that was fitting quite well, the flux rope structure that like with this bell shape. Actually, it's not what we find in a statistical study. And we also observe this decrease of the speed, so this linear trend in the magnetic ejecta, which is often interpreted as the radial expansion of the magnetic ejecta. Yes.
The 300 CMEs or so that went into this.
Sorry?
The 300 or so CMEs that went into this plot, were they taken over more than one solar cycle?
20
or?
years.
20 years, okay.
Yeah.
Cool.
So we have 2 solar cycles. But I'll talk about that just after actually effect of the solar cycle. No worries. So if there's something that you have to remember about the superposed epoch method or SEA, is that actually you get typical properties of CMs. And when I mean typical properties, that mean what is the most probable median on the mean value, profile of magnetic field density temperature. That's the way to have an idea of the typical behavior of in situ properties of CMEs. And now what we can do with that is actually, well, this has been obtained using like the more than 300 CMEs that we have in our data set. But now if you try to create some different categories of CME, we can study the effect of different parameters in the CMEs. And one thing that we want to study is actually the speed of the CME. How much does it change the properties of the CME depending on their speed? So here you have 2 categories of CME. On the left-hand side, this is what we call the relatively slow CME. So we have this delta mi parameter, which is the mean speed of the magnetic ejecta minus the mean speed of the slow we just before. So it's just the relative speed of the magnetic ejecta compared to its the local slow wave. All right. So here on the left, relatively slow, and on the right, we have a relatively fast event. And what we can see that actually we have a reinforced shift for relatively fast event. We have an increased discontinuity. We have a hotter shift. So like the heating due to the compression is enhanced when the CME is going relatively faster, which makes sense. And we also have a broader distribution in for NP and CP, so density and temperature. So like you can see that the difference between the mode, the median and the mean, is greater. So like this gap here is like the values are spread, and this is a trace of like the not narrowing the other way, the widening of the distribution in this area. So that means that actually for relatively fast events, it's not that much like the increase of the temperature. It's not a shift of the distribution. It's a shift of the distribution plus a widening of the distribution. We also see that up in the wake. So this is the part that is here just after the passage of the CME. We see that the speed of the solar is actually affected. Still, there's a shift by around 100 kilometers per second after the passage of CME for at least one magnetic ejecta duration after the passage of the CME. That means that here, typically, any duration of the Earth is around 24 hours. That means that after the passage of the relatively fast CME, solar wind properties will be affected, disturbed by the passage of the CME for at least a day. So this is quite interesting for people that want to focus on like the study of the solar wind. If they want to remove like CMEs from their time series, well, they have to be careful that some CMEs actually last longer or disturb the solar wind for quite some time. And finally, but definitely not the last, you have the magnetic ejecta here. If you take a look at the magnetic field, we see that for relatively slow event, we have all a flat magnetic field profile. But for the relatively fast, we have this very asymmetric magnetic field. And this is actually a trace of the compression of the magnetic structures that since CMEs or magnetic ejecta are going like relatively faster, when you have this compression effect that is enhanced due to the interaction of the shift region, like since it will be more compressed by the shift, this is just like forming just in front of them. So to conclude on this, yeah.
Sorry, how many of the, so there's like 300 or something
Yeah.
CMEs, how many was the breakdown of how many perform low delta V versus
Yeah, so 80 CMEs for each, basically. So when we decide like the different values, I think like in the paper, we have 3 categories. We have low, medium, and high delta V events, and we kind of try to spread them evenly. So it will be around 80 to 100 for each. So now, okay, so little conclusion about the statistical study. Like the superposed epoch methods allows us to have typical properties over certain sets of CMEs, and then choosing different categories wisely allows us to highlight some particular effects, some parameters that impact CME properties. For instance, I just showed that the relative speed of the CME actually must be an impact on the asymmetry of the magnetic field profile, while in orange you have the relatively fast CMEs, where you have this magnetic field, asymmetric magnetic field profile, and the fat profile for the relatively slow CMEs. Then we also studied the effect of the solar cycle. We just like we run the superposed epoch methods on CMEs emitted during the quiet phase and the solar quiet phase and active phase of the solar cycle. And actually, mostly we didn't see any differences in the magnetic and plasma parameter, except for the speed, which during the active phase of our cycle, so this is the orange that you can see here. Actually, we have a faster CMEs, but which is mainly just due to the fact that actually to solar wind is faster close to the Earth during the active phase. So it actually tells us that CMEs emitted during the active phase of the cycle are not that different. And even in terms of like magnitude of the magnetic field, like there's no clear differences. And about the question for numbers, we have more CMEs during the active phase of the cycle. So for that one, actually, I think we 150 for like the active phase and around 50, something like that, for like the quiet phase of the cycle. Maybe less than that, actually. Yeah.
That's a quick question.
Mm-hmm.
If maybe I remember that's right. The solar wind speed during solar maximum is higher or lower?
So that depends where you are. If you are close to the Earth at low latitudes, mostly during the slow phase, during quiet phase, you have quite slow solar wind. And then after the active phase, you have a more, homogeneous solar wind speeds. So at the Earth, it will be mostly the fastest solar wind.
But active region should have lower solar wind speed. And the quite time you have more coronal mass ejections, the latest solar wind speed should be high. I can't remember exactly, but
I think you're right, actually. That's kind of what I remember.
yeah, okay.
On average.
So maybe, yeah.
So it will be slower during the active phase?
Yeah.
Just on average,
Yeah.
Right. Well, but that's not what.
Definitely. So maybe.
Well, this
Yeah,
kind of
that's
leads into my next question. I was going to say, did you like find CMEs on their own, or did you take like the whole catalog? Because I mean, you could at active phase when they're spitting them out like
Yeah, it was.
row in row. Like, did you have to exclude some that were pretty much caught up with others in front or behind?
Yes, we try to. We try to. Yeah, so actually we base our catalog on the Richard and Kane catalog. And actually, so we removed like around 100 other CMEs where actually it wasn't that clear. So I don't think we have like the effect of other CME that could like change.
Push that higher, right? Okay.
So we should definitely discuss about that.
Yeah, sure.
So I would be interested.
Okay, yeah.
And finally, we studied the effect of the presence of flux swap signatures, mainly smooth rotation of one of the components of the magnetic field. And mostly we see a difference in the magnitude of the magnetic field. So in the orange, this is CMEs with, we call that magnetic cloud sometimes. This is why you have this MC here, but just instead of MC, read FR for flux swap. So MC is with flux swap, which is in orange here. We see that we have a greater magnetic field inside the magnetic ejecta, and we have a lower magnetic field for flux swap, CMEs without flux swap signatures. But we don't see any differences in the temperature, and actually for the other plasma parameter, we don't see any differences. Like the difference between CMEs with or without flux swap signatures is mostly on the magnetic signatures. So it tells us that mostly it seems to be like the same object that we are crossing, but just for some reason, we don't observe the flux swap signatures. So that's one interpretation. Okay, so this is a way to get information about CMEs at one point in the interquartile space. So everything I just showed you here in the statistical study part, that was at Lagrange one point using one space. But now we want to study a bit about to study the evolution of the CME properties during propagation. Why it's quite hard to do so only using one point of measurement in the interquartile space. And this is why actually we try to study CME with multi-spacecraft observation. And actually, it's like multi-spacecraft studies bring unique insight about first the CME propagation. Where actually Janvier 2019 ran the Supermass epoch analysis. So the method I just showed you, but at multiple distance from the sun. So here you have a schematic which is of course not to scale of the solar system to the Earth, where you have Mercury, Venus, and the Earth here. And she used CMEs observed at Messenger, Venus Express, and ACE. And then using the Supermass epoch method on all CMEs observed at Messenger, all CMEs observed at Venus Express, and same for the Earth. And then she studied the evolution of different properties of CMEs at different distances from the Sun. There is a Simon Good in 2019 that studied the evolution of CMEs using radially aligned spacecraft, which we also call sometimes a conjunction of spacecraft. Well, if you imagine that there is a CME going roughly that way, in that configuration, you'll have Messenger and Venus Express that are almost radially aligned. That allows us to probe roughly the same portion of the magnetic ejecta or the CME, and then you can study the evolution of this portion of the CME. But this is quite difficult because you need to have radially. First, you have to get radially aligned spacecraft, but also you have to have a CME at the right time in the right direction, and you need to have data available, which is unfortunately something that is quite a limitation. We can also study the evolution of the magnetic field, so not waiting for not looking for a conjunction, but just taking measurements done at Messenger or asteroid or B at different distance from the Sun and try to fit some evolution law that we get from theoretical studies, and then we can have some information about the evolution of magnetic field as a function of distance. And we can also have some information about the coherent scale of CMEs. In fact, Noé Elias in 2018 studied the coherence, so coherent length. So he used wind and a spacecraft, which are both at Lagrange one point, but not exactly at the same point. They have some kind of separation sometimes. And given that, he studied how he kind of estimated the coherent scale of CMEs. And what I've been doing for the last year now, using multi-spacecraft studies, was actually to use almost all the spacecraft that are in space right now. They try to quantify the aging effects. So I'm going to go through that after. So just want to do a brief story that I went over more than 4 decades of data. So you have Helios 1 and 2 that are actually quite old spacecraft here. Then you have like Parker Solar Probe, which has some very elliptical that will be very close to the Sun. You probably heard of that mission too. You have Solar Orbiter. There's also, I used a Juno and the NEAR spacecraft that are built to study small. Actually, Juno is Jupiter, right? Yeah, and NEAR is to the Eros asteroid, I think so. So anyway, my work was actually to gather all the CME networks that have been observed and trying to look for what we call simultaneous measurements. So it's even worse than having radially aligned spacecraft. It's actually having 2 spacecraft inside the CME at some point. So you have some spacecraft propagating and try to look for which CME we had some measurements at different positions inside the CME, but at the same time. And I'm going to show that actually gives us some very, very interesting information about properties of CMEs. But first, so all that to quantify what we call aging. So first, I'm going to define what aging is. Here is the events that I showed you before. So you have, same as before, magnetic field velocity and temperature as a function of time during the passage of the CME. And just to give you some, and so during the propagation, as we said before, CME might interact with the solar wind. It can also expand. And the thing is that, well, the CME, as I just said before, and as you can see here, typically the duration of the magnetic ejecta at the Earth is roughly 24 hours, and the CME takes between 2 and 3 days to reach the Earth, so to do sun to Earth propagation. That means that the time the CME passes over the spacecraft at the Earth constitutes something like 1/3 of the CME lifetime. That means that, well, since CMEs are changing during propagation, they can interact, they can expand. Well, this is what aging effect is that what is the effect of the CME evolution on the properties that were here. Like if you think about that, like typically, as we saw before, we have plenty of studies that show that typically we expect some kind of asymmetry in the magnetic field of CMEs. But what's the origin of the asymmetry? Like, is it due to the shape of CME that's formed, like the structure of the CME has like more magnetic field at the front, or is it due to some expansion that will actually produce some decrease of the magnetic field that we measure by conservation of the flux of the magnetic field? So you can see, for instance, here we have this nice bell shape here, but it's not at the center of the magnetic ejector. It's shifted a little toward the front. Well, what's the cause of this? It's just like, is it really like the shape of the CME that is due to that, or is the shift toward the front is due to expansion of the magnetic field, the time the space or force of the magnetic ejector? And a way to answer this question is to actually use simultaneous measurement. And I'm going to show you how we can do it. And actually, so after going through more, so as I said, 4 decades of data, more than 2,000 CMEs, we had one event that was actually quite nice to do this kind of study. And I'm not joking, like really, this is the one, like the precious. So you have the evolution of the magnetic field as a function of time, observed or measured at wind and year. So in wind you have, so it's in green and year is in orange. The dashed line corresponds to the boundaries of the magnetic ejecta. And we have like a very neat configuration of the spacecraft. We first have an almost perfect radial alignment, so that we have angular separation of around 1 degree between the two spacecraft. And the radial separation is such that we have a simultaneous measurement of the front and the back of the magnetic ejector. So that means that during that time here, so we first have the CME that arrived at wind, and then when wind is probing the back of the magnetic ejector, like the magnetic field properties of the magnetic ejector, the back of the magnetic ejector, actually the ME just arrived here, and here is actually probing the magnetic field at the front of the magnetic ejector. Right? I'll show you right now why it's interesting. Now, a way to quantify the asymmetry that we have here is actually to compute what we call the front to back ratio. It's just like the ratio of the magnetic field here divided by the magnetic field that you have here. Since we have like almost a linear trend for the CME, just like tells us like if you have the front to back ratio which is 1, that would mean that the profile is actually quite flat. But in this case, actually, we have the front to back ratio which is 2.1. That means that we have a magnetic field which is 2.1 times greater at the front of the magnetic ejector than at the rear, right? But during this overlapping time that you can see here, we have the measurements of the front and the back of the magnetic ejector at the same time. Like we barely have any time evolution during this time here. I think it's just like 6-7 hours, which is actually quite short. And then if we, so this corresponds to unique opportunity to compute what we call the true front to back ratio, and actually gives us a good estimation of the true asymmetry of the magnetic field profile. And then we obtain a value which is 1.4. So that means that the true asymmetry is significantly lower than the asymmetry of the original profile. And that tells us that whatever is happening, the evolution of CME properties, the time passes over. Like the time evolution of the CME properties is actually significantly impacting this asymmetry that you observe. And this is a very, very good, this is very interesting to have this kind of. And this is only, I don't think there's another way to obtain that kind of like instantaneous information if you don't have multiple spacecraft that are probing the CME properties. And actually, this is something that has been, so there's been a procedure developed by Pascal Desmoulins in 2020. Assuming some constant speed of the CME, the time crosses the spacecraft, and that we have the self-similar expansion. So it's just a way to analytically well, to describe using formula the expansion of the magnetic ejectile during the time of crossing, then you can compute the instantaneous profile. That means that instead of having a magnetic field as a function of time, as you normally have when you measure spacecraft, you can obtain, so instead of having b of t, you have b prime of x1, x prime, sorry, which are actually the spatial coordinates corrected for aging and for expansion, sorry, and then the magnetic field corrected for expansion. So technically and theoretically, this is some kind of instantaneous profile when you correct for self-similar expansion. And hopefully, well, in an ideal world, if that was completely true, then we should get 1.4 of front-to-back ratio here, right? So as a reminder, we have the front-to-back ratio of 4, and we find actually it's 1.7. So we still correct for semi-symmetry. We are like from 2.1, we're now down to 1.7. We're still good. But however, it tells us that the self-similar expansion, which is also kind of widely used expansion, because it's also quite in some way easy to use, because you have a lot of analytical formula that has been development that has been done using self-similar expansion. But the thing is that with this particular event where we are able to have this true measurement of the asymmetry of magnetic field, well, the asymmetry, so this self-similar expansion does not capture the whole asymmetry of the magnetic field profile. And this is something that has been found also by Regnault and Liu in the paper she published in 2022, actually using some fitting methods, where you cannot explain the full asymmetry of the CME you observe. And in most of the CME studied in Demon et al., when they developed the procedure, they found actually the asymmetry, the self-similar expansion cannot explain most of the asymmetry that we observe in the CMEs. So to conclude, characterizing the 3D time evolving CME structure is a hard task, given the fact that right now we only have in situ measurements, and most of the time we only have one in situ profile of the 3D of the CMEs. But we can use reconstruction methods, which works well actually with simple CMEs. But the fact is that most of the CMEs will not be simple. You have like a lot of like small features, or they can be distorted when they interact with some features with distorted ways. And actually, they're not ideal with only one in situ profile. And actually, that could be greatly improved using multi-spacecraft measurements. I also showed that statistical study really help us to have some insights about the effect of some parameters on the CME properties, but to be able to run some statistical study, we need enough CMEs. And the time evolution, so in terms of the aging effect of CMEs can impact the properties that we deduce, like the asymmetry of the magnetic field we observe in the SEA. So like with the result of the superposition methods on all CMEs where the magnetic field was asymmetric. So but we still have the aging effect inside this profile. And finally, show that multi-spacecraft studies bring unique insights on CMEs. In fact, on the aging also tells us, I didn't talk about that today, but also shows us how local some properties we deduce, such as the asymmetry of the magnetic field, can be very local. So just like 6-7 degrees away, we don't measure the same asymmetry of the magnetic field at all. It also raises like the question about the coherent scale of magnetic field structure when they propagate it into much space. But they are rare. I mean, they're quite rare. I mean, even just finding some conjunctions, like you don't need to have both spacecrafts inside the CM at the same time. Actually, they are quite rare. And right now, when we have data to do some multi-spacecraft study, well, actually, we're just being lucky. And then this is why actually right now there is a strong call the heliospheric or CME community to have a mission, space mission that's dedicated to the study of CMEs. And we'll have multi-spacecrafts that we can, on a regular basis, have CMEs with multi-spacecraft measurement. Well, thank you very much. And if you have any questions.
Yeah, thank you, Florian. Do you have any questions in the room or online? Nick?
Yeah, I had a question about the reconstruction.
Yeah.
So with these different like cross-section profiles that they use, where do they come up with these like the distorted cross sections? And is it possible to even start with a fit of the magnetic ejecta and sort of work backwards to.
But you mean like to use observation close to the sun? Is that what you mean? Or
So here, the way I understood it is you kind of choose these ellipses or distorted ellipses, and then that yields a fit for this region.
so you have three different shapes, or you tell me if I'm saying it's pretty wrong.
I was going to say, I think you can.
Well, I'll give you a shot. That's right. Give it a shot and you tell me. So like you have three different models that correspond to three different shapes.
Yeah.
And so you have different equations that you are then you are doing some fits on using these different models actually. So you have like you assume a shape of the cross section and then you perform a fit and you try to find the components.
Yeah, is there any way to like start with trying to fit the data and trying to work backwards?
So there's been a paper published by so there's Anif Chinchilla that actually developed a model which it's actually quite right now they are not doing any fitting, they just published the model that is we have three components of magnetic fields and how we can parameterize like the global shape of the cross section using just the components of magnetic field. How because it can be what we call the pancake effect. So it could be like just compressed like that, it could be compressed like that. And we have some even like the shift of the core. So they just published that, but they still haven't, as far as I know, shown any methodology to use this model to be able to fit it to the data. Because there is also one thing that I didn't mention, but like you at some point you have so many degree of freedom that you're going to fit whatever shape you have. So this is something like you have to be careful. I'm not saying like everything like just this is something I have to keep in mind. Like you want to add some extra parameter, you want to like be able to fit to some like really like crazy shape in some way, like some fancy shape. But at some point you have to think about, okay, well, but that's how certain am I that this is the unique possibility.
Can I add with the kinematic and distorted models? So they actually started life as nice cylindrical things near the sun. So you'll notice it says kinematically distorted. So we've inserted more of a round cylindrical flux rate cross section near the sun, and then we've hydrodynamically, not fully MHD, let the solar wind speeds deform it into those shapes, which are then what you get closer to 0.81 AU, and then that's the resulting field from that. So maybe that ties into not working backwards, because yeah, that naturally deformed that way. So yeah.
I'm curious why you use the front back ratio specifically for the fingerprint of the age of the CME. Why not like something else, like a roughness parameter that shows the scale of the spikes or something?
Well, the thing is that we want to be able to compare information of the normal profile and the information that we can get from the ejecta at a certain time. And right now, the only information that we have about the magnetic ejecta instantaneously is information at the front and at the back. So this is why the front to back ratio is useful. But in the it just like imagine like you have so actually you just imagine like this is some kind of real profile, but you just have information here and you just have information here. What can you do about it? Well, front to back ratio is a good way to do so. But to be like we like out like we found 19 close 19 simultaneous measurements, but only one was as neat as we found with like good CME signatures. So this is why this is like the unique, the only one. But out of the 19 close conjunction, we compared the overall asymmetry with the front to back ratio, and we found a very good correlation between the two. So that means that even if you just have information of the front and the back, you still describe quite well the overall asymmetry of the profile. We have like some correlation number about 0.9. So yeah.
And then other small question, is that period at the very end on the near data, is that missing data or is it just very?
That's missing data.
Okay.
Yeah, no, that's missing data. But we know that that's missing data. And actually, to be fair, the end of the boundaries, we just have few points before this magnetic field. But we don't care that much about that one because we just care about the beginning of the magnetic ejecta. But yeah, that's missing data. Yeah,
but at least you have the information about the magnetic field at the very end.
Exactly. Yeah, at the very beginning. But yeah, this is kind of thing that can happen. You can, I mean, just imagine this shift shifted at 209. I don't know, 20 hours. I wouldn't be giving this. I wouldn't be presenting this like that. I wouldn't have any event like that. Yeah, data availability is like a real nightmare. Yes.
When where you perform the statistics method,
Yeah.
where you looked at the 300,
Yeah.
some CMEs examples. I'm just like picturing you just going over it. Oh, I'm gonna call this part sheet and call this part, but you must have some sort of like the algorithm detecting.
No. So what you just said there, like this is the sheet. I did that twice for 500 CMEs. So yeah, no, there's no magic stuff.
Wait, but you could. But there's like a sheet, as you saw some of the good examples. So, significant increase in the magnetic fields. You can maybe implement that.
So okay, so this was the ideal world. So I showed you how it was working. Okay, so now if we go a little bit into detail, when like CME signatures, like with all the theory that we have here, like we can physically explain why these regions have these signatures and everything. Well, the discontinuity is sometimes not even here, but you still see some increase in the magnetic field, but you don't have this discontinuity. Sometimes look at what's the temperature is doing here. Like, why is it so hot here? You don't, we're not able to explain it like just locally here, but we still have this nice decrease of the magnetic field. And here you can start the change in the components of the magnetic field and like the increase of the magnetic field. So certainly the magnetic ejecta starts here in variable, even though you're very happy with the temperature. Like there is, yeah, look, there is no choice. Actually, this was part of like my internship. Like I started science doing kind of like that, like going through 500 CMEs, clicking, okay, this is where I would define the magnetic ejecta. Then after talking to my supervisors, no, that's not it. That's not it. We should change it. And then after I went through together. So that, yeah. I'm still here.
I was joking.
No, this is why that was funny actually. No, but to be fair, people start to use deep learning processes. Like we start to have quite like around 2,000 CMEs right now. So it's not that big for deep learning, but still we can try to get like try to automatically detect some CMEs, but like the accuracy is really not as good as we can have. Like even scientists are fighting for boundaries like for plus minus 2 hours, something like that. With deep learning, that will be much worse. But what's like, so I mentioned the Richardson and Kane catalog. So the way he did it is that actually he went through all the data and he looked for low temperature region. That was the main institute signature. You just like went through, okay, when when the temperature is very low, lower than a certain threshold, this is kind of a suspect CME candidate, let's say CME candidate, and then let's take a look at the data. And if it's not the CME, I'll just remove it. But that's the way like you just went over the data quickly. But what I did was actually go through 500 CMEs. I didn't look for like data by myself. I used, based on the Richardson and Kane, I used like their catalog as a basis. I went through all the CMEs, removed some of them because I kind of disagreed with some of their signatures of the fact that it was CMEs. And then after we built this catalog. So yeah, but now the version of their way to do it.
There's a
I have
question.
two questions, very nice talk. And my question is about your time aging effect.
Yeah.
It's very beautiful. You have kind of simultaneous observation.
Yeah.
And my question is that, is it possible that your ratio is influenced by how you identify your CME boundaries? I mean, for example, the real boundary or the end of the CME.
So for the from go ahead there, finish.
Yeah, just that question.
Okay, so for at some extent, yes. However, we have like this very nice increase of the magnetic field. So like the front of the magnetic ejecta here, we have like I think it's quite well defined.
Yeah, but
The end of it, something that you have to keep in mind that we don't only have magnetic field profile, we have other other data with like temperature, density, velocity, but actually is probably mostly why we decided to do this boundary here and not before. But I don't have like the plots here that I can show you to after. But yeah, we can be a little bit like impacted. Yeah, you are right.
okay, cool. And the second question is back to your proposed analysis. you mentioned that the solar wind speed will be influenced by the pattern of the CME.
Yeah.
But how about the solar wind number density? Is it different or no? Because due to the scale, we can see it. If we assume that the CME wind propagated to as well, the solar wind plasma outside, then it should be awakened after the CME.
So what you can see is that, for instance, so here you have the density, and mostly after the passage.
Yeah,
So here it's mostly like
constant.
But however, what you can see is that we have this small peak here, which is doesn't last very long. Sorry, but that could be like that is not very here, like that's not really here. Sorry, at the end of the magnetic ejecta for relatively fast movement. So you could interpret that actually as some overtaking, like accumulation of solar wind behind the magnetic ejecta that is overtaking the ME. Like, but mostly after we don't have that much effect of the passage of the CME density, nor in temperature actually.
Yeah, but why is it supposed to be?
Good question. Well, to be fair, since like you have this magnetic field, the CME that will like, it basically just opens the way to solar wind. Like just after the CME, mostly you have open magnetic field lines. Like and you will have like you will remove most of the solar wind materials. Like for the solar wind that is just after the CME.
So my question is just based on your sentence that you removed solar wind material, so we may expect a vacant space after the CME. But as you show for the number density, we cannot see.
No, we don't have any
decrease of the number density. So
in even that case, since that's a good question, but on the other way, you could also expect an increase of the density because you have solar wind that will accumulate just after the CME. And this is something that we see quite clearly after some CMEs, but not all of them. And actually here, superposed epoch method tells us that this is not something common to most of the CME in this category. But yeah, it's a good point.
You said you only had one event, right? Do you know off the top of your head if a lot of the ones that you had to throw up because of the sync event? So like,
I have the numbers. So this is a slide. Yeah, actually, I quite like the slide. It's a bit sad. Okay, so using 7 CME lists. So like that's different catalogs. It just like tells when does the CME start and when does it end, right? All these correspond to more than 2,000 CMEs, like spread over more than 40 years over 11 spacecrafts. Now, if you try to look for what we define as close conjunction for some time, but you can also like refer to as simultaneous measurement. So we just look for events where we detect a CME. So a CME like is in the catalog, and we have a radial separation between the spacecraft that is S 0.2 AU. So that's the typical size of the magnetic ejecta across the Earth, and you have an angular separation which is less than 10 degrees. Well, if you try to do so, well, you end up with 133 potential close conjunction, because here I do not take into account any data availability whatsoever. Then, when you remove all the events for which you don't have any data available, because, well, so sometimes, like, I'm going to talk about that after. Just want to finish that.
So how many of those are ace and win? I mean, you think that those would be the most likely.
Exactly, yeah. This is what I'm going to talk about just after. I'm going to show the schematic. But so remove data availability, the fact that we don't have any we don't have any CME signature sometimes, like CME is not that clear, like, oh, it's clear at one spacecraft, but not at the other for some reason. Well, you just end up with 98%. And now, if I just want to answer to the question about the X spacecraft, if I go to this slide, yeah, here, this one. So mostly, I don't have the number which here on at least 15 of them, involve either ace or win, because mostly like the close conjunction that we have is when either solar meter is close to the Earth, or Juno and Near actually when they are close to the Earth. So just when they left the Earth, when their data was available, or some of the time actually not. So we have like a lot of things that were probed. Well, that was supposed to be probed by Juno, but since the data was not available at that time because the mission just started, well, we don't have any data at that moment too. But most of them were either ace or wins. If you choose Near, we have A lot of them is stereo picture. We also have some interesting one with stereo A and stereo B. Actually, we have like stereo A and B both have like let's say like it's basically the same orbit at the Earth, just like with a small change in the radius, and so we kind of like more explore like the angular side rather than the radial direction like with stereo A and B. But we also have some events with stereo B and A and some other things. But yeah. And we also have some like Venice Express or Messenger with I don't know which one. Well, actually, no, we do have some with Helios 1 and 2, but since they're actually quite old spacecraft, more than 40 years, something like that, the data is not as good, so like sometimes quite hard to see CMX signatures, or the data is not as available as it can be today. So yeah. So again, mostly it was involving wind and ACE, but it's good that we have this like almost constant measurement of the solar wind, because otherwise it would be like much more difficult to do this kind of study.
Yeah. Thank you all, because I think we're over time, but that was really great to have like a nice interactive seminar here. So yeah. Thanks for it.
Thank you very much.